Hey there! In this video, I'll show you how to micro-benchmark your code. After watching it, you should be able to understand how benchmarking works and how to measure performance of any piece of code in terms of speed or memory allocations. So, let's dive into it. This time, I'm not using Unity. Instead, I'm showing everything inside a console application, and you'll see why shortly. But code is code. The measurements can be taken wherever you want as long as you understand the limitations, which I'll also explain. Let me introduce you to our case. Let's say I have a comma-separated string of numbers that I want to convert to an actual array of integers. The first thing that comes to mind is this one-liner here. I can split the input by commas, which will give me an array of strings, and then use link's select method to parse each string in this array into an integer. Lastly, I don't want to work with IEnumerable, so I'll convert it into an array. Now, in order to make sure that it works, I'll print a line to the console, where I'll join the array back to a string, but this time with a semicolon delimiter. When I run it, you can see the result is printed successfully. Since in a real game I'll probably use this code many times, I should probably move it to a static helper class or something. And I'll call mine string parser. Now, the easiest way to measure the execution speed of this code is by using the Stopwatch class. Before the execution, I can create a new instance of a stopwatch and run it in the same call. After the method invocation, I need to stop the stopwatch, and what's left for me to do is to log the elapsed time. Since I already know that the time it takes is really small, the built-in elapsed milliseconds property won't work for me as it returns a whole number. And the ticks themselves are not really representative, so I'm converting the ticks into milliseconds here and logging the elapsed time. When I run it, you can see that it took roughly 3 milliseconds. Can we declare it a success and call it a day? Well, I wouldn't make this video if that was all. Let's wrap this code with a for loop, and for now, we'll execute it only twice. I'll run it, and the second invocation is significantly faster. Let's increase the number of iterations to 10 and run it again. And you can see this voodoo in action once again. The third execution is even faster. And then it kind of settles. The reason for this behavior is overhead. And overhead is a composite term for many things. For example, in a mono or .NET environment, during the first invocation, we're hitting the JIT compiler. This means that when the method is invoked for the first time, it is actually compiling. This is why we have such a significant difference between the first and the latter executions. But it's not the only overhead we have. There are CPU cache misses, initialization logic, and sometimes even hidden initialization logic. For example, in our case, we're using link and int.parse. Both of those have their own initialization logic when we run them for the first time. In AOT environment like IL2CPP, we won't have the JIT overhead, but we'll still see a difference between invocations due to other overhead. So, in order to perform a benchmark with any statistical significance, we'll need to run it many, many times, potentially tens or hundreds of thousands of times. It should look something like this. I'll declare a variable that will hold the total execution time in milliseconds. Then, I'll increase the number of iterations, let's say to 100,000. And then, instead of logging the milliseconds, I'll increment the total time variable. And lastly, I'll log the average time we're spending on each iteration. If I run the code, we'll see the average result. So, at this point, we can package this code into a helper method and benchmark whatever we want with it. It will give us a good idea about the performance, and in most cases, this will suffice because usually you don't really need to go to smaller resolutions. Hell, even this example is so trivial that in most cases, I probably wouldn't spend time optimizing it. But If you're anything like me, you'd probably want to know the real results and see how far you can push an optimization. Thankfully, we have tools for that. In .NET, we have a library called BenchmarkDotNet that does everything we try to achieve and even more. Unfortunately, this library can't work with Unity at the moment, and that's exactly why I'm making this video in a console application. Again, it doesn't really matter where you benchmark. While the final numbers will be different for each platform, the core idea and the relative results will be the same for the most part. And for Unity-specific benchmarking, you can always use the Unity Performance Testing package, which I'll cover in a future video. So, how do we use BenchmarkDotNet? First, we'll need to install it via the NuGet package manager. And I'm doing this in Rider, but the approach is similar in other IDEs. Or you can even install it via the CLI tool. I'm just searching for this package in the registry and installing it into my project. The next step is to create a new class that is going to be our benchmark. And I'll go ahead and copy the input string from the program class here. Lastly, I need to declare a benchmark method, and I'm doing this by creating a wrapper method for my parser, parsing the input string to it, and most importantly, I'm putting the benchmark attribute on top of it. This attribute will tell BenchmarkDotNet that this method is a benchmark. And that's it! The benchmark code is complete. All that's left is to execute it. I'll delete everything from the program CS file, and then I need to run the benchmark runner class with my benchmark as a generic parameter. The last thing I need to do is to switch my build configuration from debug to release. And this is important because the release configuration strips a lot of overhead and makes our results more accurate. Now I can run the application and wait for the results to come in. You can see that a lot of things are going on here. My little method is being executed millions of times, and a lot of calculations happen behind the scenes. And here are the results. We'll concentrate on the first two columns here, the method name and the mean time each invocation takes. As you can see, it takes roughly 200 nanoseconds. In our results, we were getting roughly 700 nanoseconds, meaning that we were measuring around 500 nanoseconds of overhead. But the benchmark is only good if we have something to compare it with. Let's try to improve the link solution. Here, I have an almost identical implementation. I'm splitting the string into a string array and converting each string in this array into an integer. But this time, I'm using a regular for loop instead of select. Let's add this method to our benchmark class. The logic here is the same. I'm just wrapping the static method and adding the benchmark attribute. Now I can run it and wait for the results to come in. This time, we can see a second row in the results table. And you can see that it's slightly faster than the previous one. But speed is not the only thing we can measure with BenchmarkDotNet. We can also measure how many allocations our code makes. And this one is really easy. All we need to do is add the memory diagnoser attribute to our benchmark class and run the benchmark again. Now we have an additional column in the results. It shows how much memory each invocation allocated. And again, we see that our second solution allocated less memory than the first one. But what if I told you that we can do a lot better? Take a look at this implementation here. It's really similar to the previous ones, but this time I'm using multiple spans to reduce allocations. I already have a short on this, but I'll probably do a full-length video on spans in the future. For now, just know that span is a lightweight, stack-friendly view over continuous memory that lets you safely work with slices of arrays or strings without allocating. So here, I'm converting my input string into a span. Then I'm allocating an array on the stack, which means no garbage collection. Then in the for loop, I'm calculating the start and the end position of each number sequence. Basically, a comma or the end of the input string tells us that we've reached the end of the sequence. Then I'm taking the resulting sequence again as a span and trying to parse it into an int, just like I did previously. Lastly, I'm converting my buffer span into an array. Let's also add this to the list of benchmarks and run it. And you can actually see how much faster it became, because we've used mostly stack memory, and along with it, the allocations dropped to only 64 bytes. This is actually the size of the array we're creating at the end. Can we go faster than this? Yes, we sure can. We can introduce cache to avoid allocating the same array over and over again. We can also create a custom int parsing logic, and depending on how much safety we can omit from this logic, the speed will increase proportionately. By the way, I'm already implemented a couple of faster solutions, and you can see the benchmark results on the screen. If you want to see the code behind them, I'll leave a link in the description. Now you know the basics of performance measurement for your code. If you haven't watched it yet, check out my previous video where I explain how to approach performance optimizations in general. And in the upcoming videos, we'll explore even more ways of measuring performance, dive into specific cases, and learn how to work with profilers. If you found this video helpful, don't forget to hit those like and subscribe buttons. Keep on creating, and I'll see you in the next one.